Hello everyone. Today we will discuss phase and phase difference. So let us understand what do we mean by the term phase. By the phase of an alternating current, we mean the fraction of the time period of that alternating current which has elapsed, that is, which has passed since the current last passed through the 0 point of reference. That is, by phase of an alternating current, we mean how much fraction of time period of that alternating current has passed since the current last passed through the 0 point of reference. For this, let us consider the example in the figure 1. This is the figure 1. So from this figure, we find that the phase of the current at this point A is T by 4 or pi by 2 radians, because this is we are taking the time 0 as the reference time. So this wave has passed this much time when it has reached the point A. So the phase of this wave at this point A is T by 4 seconds, or in terms of angle, the phase at this point A is pi by 2 radians. Here T is the time period, that is the time taken to complete one cycle is called the time period. So from this graph of current versus time, we find that the phase of this alternating current at point A is T by 4 seconds. Similarly, the phase at this point is T by 2 seconds, and the phase at this point is T seconds. Similarly, let us consider the phase of the rotating coil at the instant shown in the figure A. So this is the rotating coil. We have to find the the phase of the rotating coil at this instant. This is taken as the reference. So this coil has passed this angle. So the phase of this coil is theta is equal to omega t. This is the phase of this rotating coil when it is at this position. Now in electrical engineering, we are more concerned with relative phases rather than phase difference between the different alternating quantities rather than with their absolute phases. So we are more interested in phase difference than in the absolute phase of any alternating quantity. So for this, let us consider two single turn coils of different sizes which are arranged radially in the same plane, and they are rotating with the same angular velocity in a common magnetic field of uniform intensity. Let us see the figure. So as you can see in this figure, we have taken two single turn coils. The first coil is this coil. This coil is coil A, and this is the second coil B. That is, the size of coil B is more than the size of the coil A. So we have taken two coils having single turn, that is, both the coils are single turn coils, but they are of different sizes, and they are arranged radially. In the same plane, and they are rotating with the same angular velocity omega in a uniform magnetic field. That is, we are rotating both these coils in this uniform magnetic field with the same angular velocity omega. So when we rotate both the coils in this magnetic field having uniform intensity, then EMF will be induced in coil A as well as in coil B. And we find that the EMF which is induced in the coil A and B will be of same frequency, and the EMF will be of sinusoidal shape. Although the value of the instantaneous EMF induced in both the coils will be different, but both the EMFs will reach their maximum value and zero value at the same time. So let us see the graph of the EMF induced in both the coils. This is the induced EMF of the coil A, and this is the induced EMF of the coil B. So from this figure we find that when the induced EMF of the coil A is 0, then the induced EMF of coil B is also 0. When the induced EMF of coil A is maximum, then the induced EMF of coil B is also maximum. Again, when A reaches 0, then the induced EMF of the coil B also reaches 0. Similarly, when the EMF of coil A is maximum in negative direction, then the EMF of the coil B is also maximum in the negative direction. Again, at 360 degree, both the coils have 0 EMF induced in them. So we find in this case that both the coils does not have any phase difference between them. That is, both the coils are in phase with each other. That is, there is zero phase difference between coil A and coil B. There is no phase difference, that is, there is zero phase difference between coil A and coil B, because both the coils reach their maximum value and zero value in the same time. So as you saw that we have considered two single turn coils which are of different sizes. We have arranged them radially in the same plane, and we are rotating both of them with the same angular velocity omega in a common magnetic field of uniform intensity, as a result of which EMF will be induced in the coil A as well as in the coil B, and the EMF induced in both the coils will be of the same frequency, because they are rotated with both of them are rotated with the same angular velocity, and the EMF induced in both the coils will be of sinusoidal shape. But since the coils are of different sizes, so the value of the instantaneous EMFs induced in both the coils will be different. However, the two alternating EMFs will reach their maximum and zero values at the same time, and the EMFs induced in the coils A and coil B will be, the EMF induced in coil A will be EM1 into sine omega t. Similarly, the EMF induced in the coil B will be EM2 into sine omega t, where EM1 is the maximum value of the EMF in the coil A and EM2 is the maximum value of the EMF in the coil B. Such type of alternating voltages or currents which have the same angle. Here also we find that the angle is omega t, and in the second case also the angle is omega t. So both the EMFs are having the same angle. So there is no phase difference between the two induced EMF. So such types of alternating voltages or currents which does not have any phase difference between them are said to be in phase with each other. That is, in this case, both the coils A and B have zero phase difference between them. That is, there is no phase difference between them, or we can say that both the induced EMFs, that is both the alternating voltages or the alternating current of both the coils are in phase with each other. So this is what we mean by phase of any alternating quantity.